Good morning, grade 12. I just want you to know I'm trying to incorporate a lab today with your notes. And so if the notes go a little bit wonky midway through the lesson, just be patient. I'll get it all figured out. So on Wednesday's lesson, I asked you to look at, for homework, 3 solutions and their appropriate changes with pH indicators and determine what the pH was approximately for each of the 3 different solutions. So if you looked at the data that you would have written down, you would have seen for solution A, you had 4 indicators, and these were the colors they turned. And then you would have looked on your periodic table on the back of your periodic table where the pH indicators are listed, and you would have noticed that if methyl violet turns blue, then that means it has a pH of 1.6 or higher, the solution. So what I usually do is I start off with some sort of a number line and I write down the first clue. So the first clue says the pH is 1.6 or higher. Then the next clue says it's 4.4 or higher, okay? So that 1.6 is no longer valid. 4.4 is the lowest that it can actually be because of the color change of methyl orange. So now we know the pH range for the solution is 4.4 or higher. Then methyl red says it has to be 4.8 or lower. Well, that's okay. 4.8 or lower still would include that 4.4. So again, 4.4 or higher. And then this says 4.8 or lower, so it's somewhere in that range. And then the last clue says 8.2 or lower. Well, I know I can't put 8.2 because it says that the maximum I have in the third example is 4.8. So therefore my range for pH for this unknown substance is between 4.4 and 4.8, and that's where those numbers are coming from. I won't bore you with doing all of them, but if I just got you started on the next one, you can see what the final answer is, between 6 and 6.6. But if I just looked, it says indigo carmine is 11.4 or lower for this particular solution. So there's 11.4 or lower is its pH if the solution is blue, okay? Or 6.6 or lower if it's indeed with phenol red. So that means it can no longer be as high as 11.4 because of phenol red, it only can go as high as 6.6. Now, when you put bromocresol green indicator in the solution, it turned blue. And that only happens if the pH of the solution is 5.4 or higher. And we know it can't be higher than 6.6 because of clue number 2. And then lastly, methyl red will, when added to the solution B, will turn yellow. And according to our list of indicators, that only happens if the pH is 6 or higher. So again, it can't be 5.4 as the lowest. It has to be 6 as the lowest. So what you're doing is you're taking the same solution, but you're mixing it with different indicators each time and seeing what effect it has on the color. Then you're looking at your pH indicator table at the pH ranges and seeing if you can somehow find where the range of the solution fits in. Hopefully, you got between 3.2 and 3.8 for the last one. If you didn't, please reach out to me on Teams so I can explain it better one-on-one. Today's lesson is all about buffers. Buffers are solutions that are made of weak acids and their salts, or weak bases and their salts. Now, I personally find it a little bit easier to explain a buffer as being a substance made of an acid and its conjugate base, or a base and its conjugate acid. Now, we learned last week that conjugate acid-base pairs differ by an H, or a proton that keep getting moved back and forth. So if I look up here at some examples of buffers, we can have what's referred to as an acidic buffer. And that's when we have a weak acid, in this case acetic acid, and its conjugate base. So it still has the CH3COO, but it's given up that proton. And so now we have its conjugate base. We can also have what's called a basic buffer. And the example we have here is ammonium hydroxide, and you can see there's the base, hydroxide, and it has given that OH up, or it's left to join with the H in the water, and now we have ammonium chloride. So again, conjugate acid-base pairs are buffers. And you're saying, great, Mrs. Day, that's awesome. What do we need buffers for? Buffers, if you haven't already heard in your biology classes, buffers are incredible chemical solutions that help maintain the pH of a system. So, for example, you have enzymes that you talk about in biology class within our body that help us have our bodies running tickety-boo. Human blood has a buffer in it that maintains our pH of 7.4. If that buffer didn't exist, even drinking a glass of orange juice could kill us. Okay, so these are examples of buffers in our bodies. So this one you'll see 2 hydrogens with a phosphate group and 1 hydrogen in the phosphate group. And that hydrogen just gets bounced back and forth. So this is the acid and its conjugate base. That's a buffer. Another buffer, very common one, carbonic acid, H2CO3, and its conjugate base, the H again moving back and forth. So these are buffer systems. And again, they maintain the pH. And they're used, yes, in our bodies, but in a lot of other chemical situations. If you add an acid to this solution, this buffer will maintain the pH for a very long time at relatively high concentrations of acid being added until it hits what's called its buffer capacity. And then once that happens, the pH will drop. Once that happens, if you're indeed placing this in with an acid and you continue to add more acid and more acid, if the pH does eventually drop, the buffer has hit its capacity, it means the conjugate base has all been used up. If you conversely put this buffer into a solution and gradually increase the amount of base, eventually the buffer will reach its capacity and the pH will start to climb significantly. And that's because you would have exhausted all of the acid in the buffer. So I'll go back to this slide. I'm just asking you here to predict the weak acid conjugate base pair buffer reactions for this. So there's your acid, there's its conjugate base, and you can tell that because it's given up its H. If you put that pair in acid, the base portion will accept that proton and keep it so it's neutral. So there's your water, and then it's just converted itself from the base to the acid. If you actually put that buffer in a basic solution, then the acid in that buffer is accepting the OH to form water and forming the X minus. And this just keeps going back and forth, keeping the pH neutral. So that's how buffers work. So what I thought it would be fun to do is to actually make a buffer. This is a lab that you usually do if you were in KV High. You usually do this lab. And I thought, if possible, I would do the lab for you and videotape it so you would know exactly what a buffer was and you would have somewhat the experience of being in the lab even though you weren't in the lab. So here's what I did. I was able to get into the lab, which you'll hear about in the video, and I grabbed as much of this equipment as I could. I have HCl, sodium hydroxide, I have NaH2PO4, Na2HPO4, so you can see how they're differing by a proton. Okay, so that's what I used for my acid-base pair. And I made up the solutions, which I will explain in the video. I had a buffer solution and water, and I had the same buffer solution and water. There were no buffaloes involved, okay? And what I did was I took a 40 ml sample of the buffer and I kept adding drops of acid, adding more acid, adding more acid, adding more acid to see if the pH would change. I took another sample of the same buffer and I continually added base and more base and more base to see if the pH would change. And then I took a sample of water and I added acid, acid it and continually checked its pH. And I took another sample of water, which I don't have drawn here, and I added base to it. And I compared what happened with adding acid to the buffer compared to adding acid to the water. What happened when I added base to the buffer compared with what happened when I added base to the water. Now, I did not show you the entire lab because I worried you would have fallen asleep. So I show you what happens initially after quite a few drops. And then I give you a few closing statements that lead you to better understand what would have happened.
Things. First of all, I got these two chemicals. So these two chemicals are sodium dihydrogen phosphate and sodium hydrogen phosphate. And so what you're supposed to notice is they only differ by an H. That's today's topic. We're going to talk about buffers. So buffers are made up of two compounds with a conjugate acid-base pair. And remember, conjugate acid bases mean they only differ by an H. So what's going to happen, we're going to do this reaction, and these two chemicals are just going to keep passing that proton back and forth. So the first thing I had to do was make up one buffer solution, but made of two components, okay? So I needed a 0.1 molarity buffer solution made of these two things. So the first thing I had to do was figure out, okay, if I'm making 100 mils, there's my 100 mils, and I needed a concentration of 0.1 molarity, how many moles of each was I going to use? So I needed 0.01 moles of my sodium dihydrogen phosphate. And this, as you can see, is a hydrate. That's why we have two waters attached to it. So I looked up the molar mass of this entire ionic compound, 156.01 grams per mole. So that means to have a 0.1 molarity concentration, if I want 100 mils, I needed 1.56 grams of that chemical. So I took 1.56 grams of this chemical. I used my balance. I put my weighing boat on the balance. I pressed tare, so this was 0. I added 1.56 grams of this. I put it into a beaker, dissolved it in 50 mils of water. Remember, half the final solution. Dissolved it in a beaker, and then I used a funnel and a stirring rod, and I channeled the solution into the volumetric flask. And that's how I made my buffer solution. So there's my buffer solution. I've already discarded the volumetric flask that it was in. There's my buffer solution. I will remind you how to make a solution before we do titrations, but for your buffer lab, that's it in a nutshell. I did the same thing for the sodium hydrogen phosphate, except I needed 1.78 grams of it. So I took 1.78 grams of it, again, put it in the weighing boat, etc., etc., but both of these went into one volumetric flask. So this buffer solution is both of these mixed together in 100 mils, okay? So that's what we did. We made up this buffer solution with those two chemicals together in the same solution, only differing by an H. Now, here's what our goal is. Awkward. Okay, here's what our goal is. We're going to see what happens when we add HCl to the buffer. We're also going to see what happens when we add sodium hydroxide to the buffer. And we're going to add hydrochloric acid to distilled water and sodium hydroxide to distilled water and see what happens. And we're comparing the change in pH. So, for an example, and thank you very much. Shout out to Callista Lyons. She is our camera person for today. So if you know Callista, I want you to reach out on Facebook, Snapchat, Instagram, Vimeo, all those other cool social medias that I don't know, and tell Callista she did a great job. Okay, so here is my pH paper. And as you can see right now, it's registering, about a 6, like neutral. 7 is where it should be, but this isn't the freshest of pH paper. Anyway, what we're going to do is dip it in the water, and then we'll compare it. And I don't know about you, but I would call that a pH of 7. So I'm going to write under pH of water with 0 drops of anything added to it, 7. Now, I'm going to do the same thing with my buffer. I'm going to add my pH paper to my buffer, and I'm going to compare its pH, and you should be seeing it's the same, 7. Okay, so buffer right now has 7. Now, I am going to take my buffer, and I'm going to add 2 drops of HCl. 1, I think that was 2. Anyway, now we'll do 2 drops of HCl to our water. 1, 2. I've just added 2 drops of HCl to the buffer and 2 drops to the water. And gave them a little stir. So after 2 drops of the HCl, I can look at the buffer and it's still a pH of 7. So we'll put that in our little chart. Buffer after 2 drops of acid is pH 7. Now I'll test the pH of the water. And when I look at it, it's changed a little bit in color. I would say it's probably between the 6 and the 7. So I'm going to record it as, what do you think, camera person? 6 or 7?
Like a 6.
6? Okay. And if we were in the school, I also have pH paper that is a little bit more precise. It goes to the nearest decimal place. So this is just giving us a ballpark figure. We also have at school a pH probe that we could dip into each solution, and that would be a bit more precise too. All right, so now I'm going to add 2 drops of HCl, 1, 2, and 2 drops, 1, 2, and I'm going to give that a stir. So there's my buffer, there's my water. So let's see what happens in the water. First, I drop it in, and I look at my pH. What do you think? 5, 6?
Can you say 5.5?
Yeah, let's say 5.5, sure. All right, so that's my water. And then let me try my buffer. I'm twisting this around so my fingers aren't in the way.
Yeah, 7.
It's still a 7, isn't it? Yeah, look at that. That buffer is holding on. It does not want to drop that pH. All right, so you know where I'm going next. 2 drops of HCl, 1, 2, I think that was 2, and 2 drops into the water, 1, 2. Now, I want to know what the water is acting as right now. Think, think, think. The water is acting as our what? It's a C word, so be thinking, what is the water? What is the purpose of the water? In an experiment, you need something in order to help you compare or analyze your results. And that is what the water is doing for us. So it's a C word. All right, so here's after 2 more drops. I think maybe a 5, I don't know. Do you think?
A 5 now.
Okay, so let's call that, oops, I missed the garbage, but that's fine. That's a 5 for water. And let's see what our buffer is at. Look at that buffer. What a critter. Holding on for us. So that buffer is still at 7. So even though we're adding equal amounts of acid to the buffer and to the water, it's only the water, which is our control. There's the word, the C word. Water's our control. So we're comparing the effects of HCl on the buffer by comparing it to the water. All right, so there's 2 more drops. And provided my fingers work, okay, maybe not, let's try this one. So here it is after 2 more drops in the water.
4.
I agree, that's the 4. So water is now dropping to a pH of 4. Now what we should have done to start with, we should have checked the pH of the pure HCl to start with and the pH of the sodium hydroxide to start with, but I can do that after a second. All right, this is our buffer. Look at that, I am so proud of that buffer. It is holding back. and it is still at a pH of 7. Okay, you know where I'm going next? 1, 2, 1, 2. Give it a stir. So we have natural buffers in our body, in our blood, and they help us maintain our pH. Very, very important, because if our pH gets out of whack, it could really cause damage to our organs. All right, so here it is with the water.
So that 4.
Yep, that is a solid 4. So there's that. And then we will add it to, or sorry, test our buffer.
The 7 still.
Yeah, I think so too. Alrighty. I will fill in the rest of these numbers before I post the video. Anyway, okay, HCl, 2 more. 1, 2, but you know I'm adding 2 each time, so 1, 2. Stir, 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 stir. I should be using half of this pH paper. I'm being wasteful. All right, here's our water. Ooh, I see a jump there.
A 3.
Yeah. Look at that, starting to get pink in there. Oops. 3. I'm gonna have to make sure I clean this kitchen counter well. All right. And let's try half a piece in this buffer since we do have another experiment to do.
Yep. The
Still 7. All right, 2 more drops. One, 2. 1, 2. So again, if you were at KV and you were doing this yourself, you would have had to have made up the buffer solution. So again, these 2 solids together for 100 mils. And then you would have had the strong HCl in the fume hood. You would have had to dilute it down. Sodium hydroxide is actually pellets. You would have dissolved it in water and made up your solution. And then you would be using pH paper just like I am. So this is water. Where would you say it? I think it's closer to 2 now.
Yeah.
Yeah. Alrighty, so let's put that down before I forget. Now, think about the pH curves that I've been showing you so far this week, and you'll note there's a limit to how long that buffering action happens. So right now, our buffer is still holding strong at 7. But it eventually will reach what's called its buffer capacity. And once it reaches that capacity, then when I add HCl, it will take a significant drop in pH. So obviously it hasn't reached its capacity yet. It can still keep fighting off this HCl. Alrighty. So in the water, I'd say still a 2.
Yep.
And getting tinier and tinier. There we go. All right, still a 7. Okay, now myself as well as, what was this? It was still a 2, I think, wasn't it? Yeah. Okay, so myself and probably my camera crew getting a little bit tired and tedious of this. So let's do 6, 8, 10, 12, 14. Now let's just, for the gags, let's instead go all the way to 20. Oh yeah. Look at that. That's a big jump. All right, so let's add 4 drops this time. 1, 2, 3, 4. 1, 2, 3, 4. Stir, stir. A, I'm worried about boring you, and B, I'm worried about running out of pH strips. So let's just see. So there is, I'd say probably still a 2.
Mm-hmm.
And let's see if our buffer broke yet.
my goodness, what a good buffer. I'd say it's still on 7. Okay, so we're going to, let me see, I'm going to add a little column up here. Let's jump all the way to 26 drops. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I think that's a 2. 2, maybe a 1. It's really teeny tiny. Oh, good. Let's get acid everywhere. Okay, there's that. And now, let's try the buffer. Oh, Lord love a duck. It's still 7. Come on. I want to show the kids what happens. All right. So, this I think we're still at 2. This is at 7. All right, let's go up to, last time we added 6 drops, let's add 10. So let's go up to 36 drops. What a beautiful data table. Don't ever pass anything into me like that. Okay, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Trivia question. Do you know how many drops are in a milliliter? Anybody know? No? In a milliliter, there are approximately 20 drops. Alrighty, so you can test me someday when you're bored, see if that's right. Okay, so here we go. Water. And I still think it's about a pH of 2. That's probably what the acid is, to be honest. Okay, and now let's see if the buffer moved yet. Oh. All right, so here's what's going to happen. We're now at 12 minutes, and you're probably a little bit bored at this point. I wanted you to see what the pH of the HCl was to start with. So I'm just putting some HCl on the pH paper, and as you can see, to start with, it's about a 1 or a 2. Okay, HCl 1. Okay, HCl is a very, very strong acid, so it makes sense. It's a pH of 1, and that's what it shows on all the pH curves in our notes as well, pH of 1. Okay, now I'll just take a piece of pH paper and show you what the pH of the sodium hydroxide is to start with. So there's the sodium hydroxide we're using. What do you think?
13.
I agree. So let's write that on our chart up here. So we're starting with a pH of 1 for our HCl and our sodium hydroxide a pH of 13, which again, it agrees with what our pH curves are showing in our present notes. All right. So grade 12, I'm just going to do a few of these. So again, we're starting with our buffer solution, our water solution. I just had to make sure they were both about 50 mils, so we're comparing things equally, okay? Now, I'm going to start, we've already done with 0 drops, the pH of the water was 7, and the buffer to start with was 7, so that hasn't changed. So now we're going to add 2 drops of sodium hydroxide. So 1, 2, 1, 2. And then we'll give that a stir, give this a stir, and we'll see if that changed our pH. So for our sodium hydroxide and water, it's hard to see, isn't it? An 8 maybe? Yeah, I think that's good. Let's call it an 8. All right, so right away, quick, with water and sodium hydroxide, the pH started to climb to an 8. And now let's do the buffer and sodium hydroxide. And you see it's still
A 7. No?
Feels like looks like a 6.
6?
In the middle.
In the middle? Okay. All right, let's add more and see what happens. So let's go up to 4 drops, so 2 more. 1, 2, 1, 2. And our water, so let's start with our water. I really need to get more pH paper.
I don't know. 11?
Sure, let's call 11. Although it looks closer to 12 when I do this.
Hmm.
Anyway, 11 or 12, doesn't matter. Let's call 11.5 just for the gigs. All right, and oh, that's clear as mud. All right, and let's do it for our buffer. Uh-oh. Okay, don't ever do it this way. This is Mrs. Tate being incorrect. Do not put it directly on your hand. All right. Where'd you put that one?
Still a 6.
Chubby little finger in the way. That's ridiculous. All right, so let's leave it as a 6. So maybe there was something in that beaker already that brought it down a little bit. But anyway, all right. Oops. So we're gonna add 2 more drops. 1, 2, 1, 2. Stir, stir.
I think it's a 12 for sure now.
Okay. 12. So I don't know if you noticed grade 12, but we didn't measure the buffer solution. I just took for granted it was the same solution, but like I said, maybe there was something in that beaker and I should have checked it initially. It was probably a 6 to be honest, because it wouldn't have jumped like that. All right, and so now we're gonna try our buffer solution.
Same.
Yeah, so it's still not moving. Okay, we'll do 1 more, 2 more drops. And this is also where the more precise pH paper would come in handy. That would take away some of the indecisiveness, or the pH probe. Either one of those things would have been handy. But that's all right. This is better than nothing. I still think you're getting the idea of how buffers work. So this is 2 more drops. And again, let's just say, like, for all these, we can call it 6, 7, whatever. It's still consistent is my point. Okay? And now we'll add this to the water.
12.
Yeah, I think it's still a 12. The paper is kind of shady, so it's hard to see in the light. All right, and this last one, this is for the buffer, and then we're out of pH paper. Take out your phones, please, and take a screenshot of this. This is tonight's homework, so you have all weekend to work on these questions. These are theory based, okay? So you don't need your calculator, but I do want you to work on them, please. I know sometimes we don't do homework because it's not, quote, for credit, but I do want you to do this, please. I really think it would help with the theory. I'm going to steal Monday's class for titration, and then we will start organic on Wednesday. For those of you who haven't noticed, I did post credit number 4 to your website today. Yesterday, Thursday. Credit number 4 is actually due Wednesday, May 27th. I thought it was important we get that one done, especially because we're starting our organic that day. Okay, so let me summarize. You're watching today's video and you're doing the homework, which is the screenshot right now, questions 1 to 5.
and then you're going to work on credit 4 assignment, which is due Wednesday. I will be online this afternoon, Friday at 1:30 if you have any questions for me. And you can also reach out to me Monday and Tuesday, and I can certainly set up a Teams meeting with you then if you have any questions for Wednesday's assignment as well. Have a wonderful weekend. It's supposed to be beautiful weather, and please hang in there. We just have to get to June 12th. You can do this. Bye.